Welcome to Bite-Size Data Science. I remember one of the first time I saw a presentation on neural networks. There was a picture of a neuron and the mention of its different components. Then there was a diagram of a neural network. From there it jumped to being able to differentiate between the Apple logo, a red apple, and a green apple. I believe the goal of the presentation was to show the importance of neural networks and that we should all get into it. It is pretty impressive what neural networks can do. Face recognition, extracting license plate numbers from a picture, translating text from one language to another. It can also help in more traditional business problems. The first step in deciding to use neural networks is to understand how it works. Let's start with a simple problem. Given the weight of a vehicle, can we predict how many miles per gallon it will achieve? I used the following graph in the very first video of this channel. It represents the use of linear regression. Many of you should remember this from high school or college, the formula y equals ax plus b, where a is a multiplying factor or weight given to the attribute x that represents the weight of the vehicle. This formula is at the core of neural networks. If we use more attributes to figure out the miles per gallon, we would need a different weight for each attribute. The attributes could be things like the weight of the vehicle, the engine class, how aerodynamic the vehicle is, and tire pressure. Let's look at the following neural network. We see that all the neurons or units are connected. This is called a dense network. The first layer we see here is the input layer. This represents the four attributes we are feeding to the network. In the middle, we have two hidden layers, and at the end we have an output layer. All three layers have a version of the linear regression formula. Looking at the formula, we can see that each unit has a number of weight parameters. Assuming that each attribute was converted to a number within an appropriate range, we are ready to go through the neural network. Each unit uses a linear regression formula. All the weights, 14 in total, are first initialized randomly to very small values greater than 0. The training starts. Note that we are in a supervised learning context, which means that for each input we know the expected result. Each unit of the first hidden layer receives the four input attributes. Since the weight used in each unit is different, they likely get different results. If we were to leave it at that, neural networks will likely be nothing more than linear regression. We have to augment the linear regression with a nonlinear function. The value returned by the unit is the result of the nonlinear function applied to the result of the linear regression formula. The same process applies to the second hidden layer and the output layer. With the output, we calculate the difference between our result and the expected one. This is done using what's called a loss function. Finally, we adjust the weights proportionally to their impact as to reduce the error we found in the generated answer. This is done with what we call an optimizer function. There is more to it than this simple explanation, but this provides a good high-level understanding. You may have heard the term learning rate. This is a value that puts a limit to the changes to the weights in each iteration. Another term is epoch. It represents the iteration over a set of input values through the neural network. The challenge of creating a neural network is to fit the model as closely as possible to the training data as to have the smallest error possible without losing generality. At this point, you should have many questions. What are the activation functions? What are the loss functions? What are the optimizers? How many layers should I use? How many units should I have in each layer? And there are many more questions. Be patient, we'll address them in due time. Now we have a basic understanding of how neural networks work and that they are not only for facial recognition. In the next video, we'll look at a concrete example of a customer churn to solidify the understanding we got here. See you next time on Bite-Size Data Science, and don't forget to subscribe.